To see that electromagnetic waves transport energy, let's take a look at this demonstration involving a radiometer exposed to a light source. A nice illustration of this idea.
All right, folks, and we're going to talk about yet another form of microscopic kinetic energy in the form of light. Now, we can think of light as consisting of little tiny particles called photons, and those photons possess kinetic energy. And I'm going to show you this by taking a look at this little device over here, this radiometer, and you'll notice that the radiometer panes are not moving right now. Because we have a shield here, none of those light particles are able to actually strike the radiometer panes. But once I remove that shield and we allow those light particles, those photons, to strike the panes of the radiometer, you're going to see them transfer some of their microscopic kinetic energy. So on the count of three, we'll remove the shield. 1, 2, 3. And notice what happens. Those photons hit the radiometer panes. The microscopic kinetic energy of those photons then makes those panes start to move. So we see a conversion from microscopic kinetic energy of light particles into the macroscopic kinetic energy of the radiometer panes. If I put the shield back in place, you'll notice that those panes quickly slow down when they're no longer receiving that microscopic kinetic energy.
In the video clip you just witnessed, I talked about the transfer of energy from the bright light source to the radiometer panes via little particles of light called photons. This is one model to describe the transfer of radiant energy taking place. But there's another model, to describe this transfer of energy. It involves a wave model as opposed to a particle model, which explains the radiant energy transfer in the form of electromagnetic waves rather than these tiny particles that we call photons. So you can see with your own eyes that according to this wave model, not only do electromagnetic waves travel from one point in space to another, but they carry energy with them. And that is where we begin today's discussion. So if electromagnetic waves transport energy, where exactly is this transported energy located? Well, it turns out that the energy is stored in the electric and magnetic fields of the waves themselves. You recall way back in our discussion of electrostatics, in the unit we did on capacitors and capacitance, we talked about the energy stored in the electric field between the capacitor plates. And we introduced this quantity that we called energy density, which was really a measure of the amount of energy stored in the electric field per unit volume. And we derived this expression for the electric field and took on the following form, The energy density, for the electric field, that is the energy stored in the field per unit volume, when like 1/2, epsilon naught times the electric field strength squared. Now, you also recall in a more recent discussion on inductors and inductance that we derived an expression for the energy stored in the magnetic field, per unit volume. Magnetic field of an inductor, I should say, per unit volume. And the magnetic energy density, could be described in terms of the magnetic field as follows, as V squared over 2 mu naught. So we see here that regardless of whether we're talking about the energy stored in the electric field or the magnetic field, the energy density, stored for each field goes like the square of the field. So what we now want to do is to determine how much of the total energy transported by an electromagnetic wave is stored in each field. In other words, does each field store an equal amount of energy? Or does one field store more energy than the other? So let's find out. So really, in order to do this, okay, what we need to do is to find the energy density of one field, okay, expressed in terms of the other field in order to make the comparison. Okay, so we are going to arbitrarily choose to find an expression for, okay, the magnetic field energy density in terms of the electric field. Okay, so what you see on your screen right now is a magnetic field energy density expressed in terms of the magnetic field. But, okay, using this relationship here between the fields, okay, that at any point in space, the magnitude of the electric field goes like the speed of light times the magnitude of the magnetic field. And we can use this, okay, and make the substitution here. Okay, so substituting E over C and for B, okay, it takes us to this point. We now have an expression for the magnetic field energy density in terms of the electric field only. Let's make another quick substitution here using the fact that C squared is equal to 1 over mu naught epsilon naught. Okay, and when we plug that in and simplify, okay, lo and behold, look at what we discover. Okay, we discover that, okay, the energy density of the magnetic field is exactly equal to the energy density of the electric field. Okay, in other words, okay, for an electromagnetic wave, the energy is stored equally amongst these two fields. We'll begin this slide by restating this important relationship that we derived in the previous slide, okay, regarding the energy density of the two fields. Okay, namely that they are exactly identical at any given point in time. For a given volume, the energy is shared equally amongst the two fields. So if I'm looking at an electromagnetic wave traveling through space, okay, we can say that the energy density of one field type must be exactly equal to the energy density of the other field type, okay, at any given point in time. Now, if we want to get an expression for the total energy density, okay, that is the energy density of both electric and magnetic fields, then we simply need to sum up the energy densities of each field separately. And since they are identical to one another, okay, it should not be surprising that to get an expression for the total energy density, we can simply take our expression for the energy density of either field and multiply by 2. So in other words, we said that the expression for the energy density of the electric field went like 1/2 epsilon naught e squared. Multiplying that by 2 gives us a total energy density of epsilon naught e squared. Similarly, we said that the energy density of the magnetic field, okay, was given by B squared over 2 mu naught. Multiply that expression by 2, okay, to get the total energy density, we get, okay, this expression of B squared over mu naught. So it's worth noting here that while the total energy of an electromagnetic wave is constant, we note that the energy density of the wave at a given point in space and time is not constant, as the electric and magnetic field values, okay, the values of those vectors, okay, their values of their magnitudes change in both space and time. Now, lastly here, we want to get an expression for the average value, the mean value of the total energy density, okay, of an electromagnetic wave. And in order to do this, we're going to have to, think back a little bit to your course in trigonometry, okay, and what you learned about sinusoidal functions, because as we know, all electromagnetic waves, really like all waves, whether electromagnetic or mechanical, okay, all waves are sinusoidal in nature. They can be described as, sine or cosine functions or a linear combination of both. So if we take a look up here at the right-hand portion of your screen, this is simply the cosine function, y equals cos x. You'll notice that it oscillates between, okay, the values of 1 and -1. and therefore would have an average value of 0. Okay, but here we're really looking at the square of this function. Notice that the energy density goes like the square of either the electric or magnetic field. So I'm now going to show you here, this is the cosine squared function, and you'll notice that it oscillates between a value of 0 and 1. Okay, so we can say that the average value of cosine squared x would really be 1/2 its maximum value of 1, okay, or 1/2. So here, if we want to find the average value of the total energy density mu, okay, in other words, the average value of, say, epsilon naught E squared, well, we can say that that's going to represent, okay, 1/2 of, okay, the maximum value of that, okay, expression for the electric field. So we can say here it's going to be 1/2 of E max squared, which is going to give us this expression of 1/2 epsilon naught E max squared. Similarly for the magnetic field, okay, because it too is sinusoidal in nature, we can say that the average value of the energy density, okay, is going to go like the average value of B squared, which would be 1/2 of the maximum value of, okay, the magnetic field squared. So we are now going to introduce this new concept to help us describe the energy involved in an electromagnetic wave. That is the concept of the Poynting vector. Okay, the Poynting vector, named after John Henry Poynting, a man whose name truly models his life's work, in that the Poynting vector points in the direction of energy transfer, as we'll soon see. So let's start by defining it. Okay, the Poynting vector, we use a capital S. Note that it's a vector, is defined to be this. Okay, 1 over mu naught, the cross product of E, the electric field, okay, with that of the magnetic field. Now, because it is a vector and all vectors have a magnitude and direction, let's start out by talking about the magnitude of the Poynting vector. So we will start by taking a look, what does it actually mean? Okay, when you take the cross product of these two fields. Well, it turns out that the magnitude of the Poynting vector is simply the instantaneous rate of energy flow per area. Now, recall when you talk about a rate of energy flow, that's a measure of power. Okay, the rate at which energy gets transported or gets converted from one form to another. That's a measure of power. When you take the power divided by area, if you remember back to your discussion of wave theory in Physics 102, okay, that is a measure of intensity. So the Poynting vector tells us something about the intensity of the electromagnetic wave at any given point in time. If we want to talk about the meaning for a plane electromagnetic wave, okay, then where the electric field by definition will be always perpendicular to the magnetic field, so we're taking the sine of 90 degrees when we take our cross product here, then we can write the magnitude of that Poynting vector, really the intensity of the wave, as either, okay, E times B over mu naught, that is the electric field at a given point in time, times the magnetic field at that point in time divided by mu naught, or, okay, using this relation which relates our two fields, we can write the Poynting vector, okay, the wave intensity in terms of either field separately, as you see here. So let me just give this statement here. Okay, once more. Note that the energy carried by the wave is proportional to the square of the wave amplitude. Okay, this is exactly what you learn when you talk about mechanical waves in Physics 102, that the energy that the mechanical wave transports is proportional to the square of the amplitude of the wave. Here for electromagnetic waves, it is no different. Okay, wave energy being proportional to the square of the amplitude, which is either of the electric field or the magnetic field. And finally, let's take a look at the direction of the pointing vector. It is very simply the direction of energy transfer, that is the direction of the wave propagation in space. Now I know that no one here likes a hand wave job. Okay, that is to see expressions magically appear out of thin air. So I promise not to disappoint you. In this slide, we're going to derive this expression for wave intensity. Okay, that is the magnitude of the pointing vector. So you can see exactly where it comes from. You're welcome. So, in order to do that, okay, we're going to take a look at this diagram you see in the right-hand portion of your screen here, where you see an electromagnetic wave that is traveling in the x direction. Okay, it's traveling through space, and it travels through the slab of cross-sectional area A and thickness dx. Okay, where the cross-sectional area of the slab at a given position x encompasses the field vectors at that particular point in space. Okay, now I think you can clearly see in the diagram that the space occupied by the wave changes in time. Okay, that while the wave's total energy may be constant, okay, that sometimes that energy is spread out, okay, and then at other times in points in space it is very concentrated. So, like I said in the previous slide on energy density, that the total energy of the wave may be constant, okay, it may be unchanging, but that the density of that energy is not. Okay, so given this diagram here, using some simple kinematics, we can say that the wave will travel a distance dx in the x direction in a time dt, okay, and distance equals rate times time, right? So that electromagnetic wave traveling in a vacuum travels at a speed c, so we're simply saying that the distance it travels in this infinitesimal time dt is given by the expression dx equals c d times dt. Now, when we take a look at the total energy, okay, contained in the slab of volume dV, okay, we can use the concept of energy density here. Okay, remember that the energy density goes like the energy per unit volume, or in the language of infinitesimals here, if we're talking about this infinitesimally thick slab with an infinitesimal volume dV containing an infinitesimal amount of energy du, okay, we can then say that, okay, the energy of the wave, okay, contained in that slab du goes like its energy density U times the infinitesimal volume dV. Now, using the expression for energy density, this is the total energy density contained in both fields from the previous slide, it goes like epsilon naught E squared, that is expressed in terms of the electric field. dV, the infinitesimal volume of the slab, is just given by the cross-sectional area A times the infinitesimal thickness dx. Okay, and here substituting this value for dx above using the simple kinematics, we can say that dx is equal to c dt. We make that substitution. Okay, and from here, we're going to divide both sides of the equation by dt. And in doing so, you'll notice that, okay, du dt is an expression for the power of the wave, right? That is simply the rate at which the energy is transported across that slab, okay? So rate of energy transfer per time is simply the wave power here. And in the next step, we're going to divide both sides by the area, and we know that taking the power of the wave divided by the area, that gives us a measure of wave intensity. And so we see here that the wave intensity has this value, okay, given by epsilon naught times c e squared. So we're now going to substitute, okay, this expression CB in for the electric field magnitude. C squared equals 1 over mu naught epsilon naught. Okay, and we're simply going to do that so that when we do so, we make our expression for the pointing vector magnitude here look like what we saw in the previous slide. Okay, we can write it as EB over mu naught. Okay, so we see here that by making this substitution, okay, we arrive at the definition of the pointing vector, that is the wave intensity, that we simply stated on the previous slide. So, okay, no hand waving here, folks. Okay, you saw where this expression comes from with your own eyes, in gory detail perhaps. Looks like I didn't tell you the full truth on the previous slide. While it's true that the dimension of the pointing vector is that of wave intensity, because the value of the pointing vector changes in time as the values of the electric and magnetic field change in time for any given point in space, that means that the intensity of the electromagnetic wave is really a measure of the average value of the pointing vector over one complete cycle. You know, when we talk about wave intensity, we want a single value for that wave. So in order to get that single value, okay, the single value for intensity, we must take the average value, okay, of that pointing vector over one complete cycle. So for a plain electromagnetic wave, okay, we can express the pointing vector like this, and you recall this was, okay, done previously here. This is an expression for the pointing vector in terms of the electric field, okay, rather than the magnetic field. And we see that because of the square that goes like the field squared, okay, this tells us that, and we know that we express both the electric and magnetic field as sinusoidal functions. Remember, we said that the electromagnetic field are wave-like, okay, but that squared factor, okay, gives us this cosine squared term here. And you'll notice that, okay, when we look at, you know, Emax here, that's the amplitude of the electric field, that's a constant. Of course, mu naught and c, these are constants, so those don't change. But, okay, because this cosine squared term here changes with both x and t, okay, that means that the value of our pointing vector is going to change continuously in time, okay, as well. So how do we end up getting the average value of that? Well, in order to do that, we need to find the average value of that cosine squared function. And as we saw in the previous slide, whereas, okay, just the cosine function oscillates between a value of -1 and +1, giving it an average value of 0, the cosine squared function oscillates between a value of 0 and 1, giving it an average value of 1/2. So, you know, very simply then, substituting a value of, you know, 1/2 in for cosine squared kx minus omega t, okay, we come up with this expression here for the average value of the pointing vector, okay, which is really a measure of the wave intensity, right? We can express it either in terms of the amplitude of the electric field, okay, as Emax squared over 2 mu naught c, or we can express it equivalently in terms of the amplitude of the magnetic field, okay, c times Bmax squared over 2 mu naught. Okay, the last thing we want to do on the slide, okay, is, okay, to be able to find this somewhat simple relationship between wave intensity and energy density. Okay, so just putting this up here, what we've seen previously, what we derived on a previous slide, we saw that, okay, the average value of the total energy density for an electromagnetic wave, okay, we expressed either in terms of the amplitude of the electric field or the magnetic field, looked as follows. Okay, so let me once again grab a laser pointer here. If we want to find that relationship between, okay, the intensity, that is the average value of the pointing vector, which we said we could express as this right here. Okay, notice C times B max squared over 2 mu naught. Okay, you'll see how closely related that is to, okay, the average value of the total energy density of the electromagnetic wave, which is expressed up here as B max squared over 2 mu naught. So hopefully you see that these two expressions are related by this factor C. Okay, that the wave intensity, that is the average value of the pointing vector, goes like the speed of light times the average value of the total energy density of the wave. So if you think you might need a little help, okay, in remembering that expression here, okay, never fear, we've got our one-eared baby rabbit here, Bongo, here to give us some insight here. Take a look at what he has to say that may help you remember, okay, the relationship here between, okay, wave intensity and average total energy density. So let's apply this concept of electromagnetic wave intensity, okay, to our very own sun. And here we are told that, okay, the average intensity of sunlight, and I should point out, as we said on the previous slide, that when we talk about the intensity of an electromagnetic wave, by definition we are talking about an average value, okay, for that wave over one complete cycle. So here we're told that the intensity of sunlight on a clear day at noon is about 1,000 watts per meter squared. And first of all, we're asked to find what the peak electric field of sunlight is. Well, on the previous slide, we showed that the intensity of an electromagnetic wave, really that average value of the pointing vector, is related to the square of the amplitude of either the electric field or magnetic field. In this problem here, we're asked to find the peak electric field strength, so we're going to start with our expression for electromagnetic wave intensity in terms of the electric field amplitude here. We're going to solve it for the amplitude of the electric field here, okay, the peak value, and we're going to plug in the numbers for these fundamental constants mu naught and C, plug in the value that we're given in the problem for the, okay, wave intensity of sunlight, okay, when the sun is directly overhead, is about 1,000 watts per square meter. And in SI units, this gives us a value for the amplitude of the electric field, okay, that is the peak electric field strength being about 870 volts per meter. In the second part of the problem, we're asked to find the peak magnetic field of sunlight. Well, remember that for any electromagnetic wave, the electric field and the magnetic field are always in phase with each other, which means that their maxes and mins, their peak values, would happen, okay, at the same point in space at the same time. So we find that these field magnitudes are related by, okay, this fundamental constant C. Okay, that is the magnetic field amplitude goes like the electric field amplitude divided by C. When we plug in the number, the value we got for part A divided by the speed of light, we find out that the magnetic field has an amplitude of about 3 microtesla. Not only do electromagnetic waves possess or transport energy, they possess or transfer momentum as well. Because electromagnetic waves travel at the speed of light, our classical definition of momentum that we discussed in Physics 101, it won't suffice here. We need a relativistic expression. Now, we're going to talk about relativity theory at the end of the course, but Since we haven't yet, okay, we're going to have to simply state the definition here, okay, rather than derive it. It turns out that the magnitude of the momentum that a wave can transfer is related to its total energy, okay, as follows. The magnitude of that momentum goes like the total energy of the wave divided by the speed of light. Now, do you think you could possibly forget that definition? Well, we're going to recruit the help of our friend Bongo here because he's quite handy with this and quite helpful. He will help us or give you a way to possibly remember the definition of momentum for an electromagnetic wave. Let's see what Bongo has to say here. He says that to remember the definition of momentum for an electromagnetic wave, just answer this question. Am I politically correct? Well, yes, Bongo, you are, okay, P, C. Yes, you are politically correct. Thank you, Bongo. Thanks for helping us remember the definition of momentum. All right, so back to our task here. Okay, we want to ask the question, so what happens if an electromagnetic wave strikes a sample of matter? Okay, to see what happens, let's revisit a topic that we discussed in Physics 101 and see the optical equivalent. That is, okay, what happens in the case of electromagnetic waves, okay, when an electromagnetic wave strikes matter. In Physics 101, I referred to this as the physics of bouncing. Okay, but it is really simply a consequence of the impulse momentum theorem. This is the phenomenon whereby if an object is allowed to bounce off of a surface, it experiences a greater change in momentum and imparts a greater impulse, okay, than if it is simply allowed to stick. So let's take a look here. In the case of mechanics, we will look at a ball which is allowed to strike a wall. Now, in the case of sticking, okay, if that ball strikes the wall and sticks to the wall such that its final momentum is 0, then the change in momentum of that ball is simply equal to its mass times its speed upon impact, v. But for the case where a ball is allowed to strike the wall and rebound off the wall, okay, or bounce off the wall, well, in the special case of an elastic collision where it rebounds at the same speed it strikes at, in that case, okay, the change in momentum of the ball is twice, okay, m times v. In other words, we get twice the change in momentum, okay, for the ball, twice the impulse imparted to the wall for the case of bouncing than we do for sticking. Now, in the case of optics, or when we look at electromagnetic waves, okay, a very similar phenomenon occurs. If we let an electromagnetic wave interact with a sample of matter, let's say with this black wall over here, where it will be totally absorbed by the sample of matter or absorbed by the wall, okay, in that case, for the case of total absorption, the change in momentum for that electromagnetic wave is simply, okay, U over C. But in the case of total reflection, that is, if we let an electromagnetic wave strike a wall, okay, to which it is reflected, let's say in this case here where that wall is a mirror or a silvered surface wall, in that case, okay, that electromagnetic wave experiences twice the change in momentum as in the case for total absorption. Just to review this, for the case of mechanics, I will show you the demo of the bouncing dart, Okay, maybe you recall this, maybe not. It's a nice illustration to see the difference between the change in momentum imparted or experienced for the case of sticking versus bouncing.
Okay folks, this is what I call the bouncing dart demo. So what we're going to do is we're going to take this high-tech dart gun and shoot a dart at this plastic box. Okay, but you'll notice that one side of this box is smooth, so I'm hoping that the dart's going to stick to it. Whereas the other side is covered with toothpicks, so we should get the dart to actually bounce off the box. Now, remembering what we're saying about the physics of bouncing, if an object bounces off another object, it imparts a bigger impulse and there's a bigger change in momentum. And in this case, I'm hoping that for the case of bouncing, we're going to get a momentum change that is big enough that we're actually going to be able to knock the box over. Whereas when we shoot the dart at the smooth side and we get it to actually stick, we get a momentum change that's only about half as big, probably not enough impulse or change in momentum to actually knock the box over. So let me set this into position and then we'll take a look at the shot. Alright folks, first we're going to be shooting at the smooth side of the box, and I'm hoping that this dart is going to actually stick to the box. On the count of 3, here goes. 1, 2, 3. Okay, now you'll notice that for this stick-together collision, the momentum change and the impulse delivered to the box was not enough to knock it over. But let's perform the same experiment to the other side of the box. Okay, whereas in this case, we're going to get the dart to bounce off of the box, supplying a much bigger impulse and change in momentum, hopefully enough to knock this over. So here goes on the count of 3. 1, 2, 3.
Thus far we've learned that not only do electromagnetic waves possess and transport energy, okay, but they possess and can transfer momentum to a sample of matter that they encounter. A related quantity to momentum is what we call radiation pressure. If an electromagnetic wave interacts with matter, in addition to transferring energy and momentum, there is a pressure that the wave exerts on the sample of matter, okay, as a result of its interaction. As you might expect, just as the amount of momentum transferred by an electromagnetic wave depends on the degree to which it is either absorbed or reflected by the interacting surface, the amount of radiation pressure exerted also depends to the extent, okay, that this energy is either absorbed or reflected. So we're going to consider both extremes. That is, okay, the case of complete absorption, okay, of the electromagnetic wave by the surface, as well as the case of complete reflection of that wave by the surface. So starting with the case of complete wave absorption by the surface, okay, as illustrated in this simulation here, okay, if that wave is completely absorbed, well, we're going to start what we talked about a couple of slides ago, which is, okay, the fact that electromagnetic waves, we said, possess momentum. Okay, they can transfer momentum, but our classical understanding of momentum is no longer valid. So what I'm showing you here is what we say is a relativistic expression of momentum. Okay, we will talk much more about this in about a week's time. Okay, but for now you kind of have to take it on faith that the momentum of an electromagnetic wave or of a photon, if we're using a particle model of light, can be expressed as U, which is the symbol for the total energy of that wave or photon, okay, divided by the speed of light. Now, when we look at an electromagnetic wave being completely absorbed by the surface, we can say that that energy gets completely absorbed, and the change in momentum, okay, of that wave and the impulse imparted to the surface, okay, is given by, okay, U over C. So when we want to take a look at radiation pressure, this new quantity that we're talking about, okay, we're going to think back to the unit that we did on fluid mechanics where we talked about pressure. We define pressure as this ratio of force per unit area. Grab my laser pointer here. And now think even further back to your course in mechanics, okay, Physics 101 here at MJC, where according to Newton's second law, the force is exactly equal to the time rate of change of momentum, okay, dp dt. And when we come over here, when we look at our expression, our relativistic expression for momentum, when we differentiate that with respect to time, okay, this is what we get. Okay, c is a constant, 1 over c times du dt. Think about the meaning of du dt. U represents the energy of that electromagnetic wave. Okay, du dt then represents the rate at which that wave's energy is being transferred. This is really a measure of the wave power. When we divide the wave power by area, we now have a measure of wave intensity. Okay, and if you recall, we said that okay, basically du dt, power divided by area, is a measure of intensity, which is really equal to the magnitude of the Poynting vector s. So at the end of the day, we see that for this case of complete surface absorption, the radiation pressure of that electromagnetic wave is given by this very simple expression, okay, S over C, S being the magnitude of the Poynting vector. Okay, so when we look at the case of complete reflection, as we see illustrated in the simulation here, okay, so the wave is completely reflected from the surface. Recall what we came up with a few slides ago where we said in that case, the change in momentum, whether we're using a particle model or a wave model for light, would be twice, okay, what it is for the case of complete absorption. So if the momentum change for complete absorption is U over C, okay, for complete reflection, it's twice that big, or 2U over C. So basically, what we're saying then is that this is going to have the same effect on radiation pressure. We can then reason that the radiation pressure corresponding to the case of complete surface reflection of the wave, okay, would have a value of 2 times the Poynting vector magnitude divided by c. One more thing I just want to point out here. In classical physics, all values between these two extremes, that is between the case of complete surface absorption and complete surface reflection, all those values in between reflecting partial surface absorption and partial surface reflection are possible. So there's a history lesson to be learned with this example. This example deals with what was called the Strategic Defense Initiative, or SDI, or as it was more commonly referred to by the American public, simply Star Wars. It was an anti-ballistic missile defense system proposed by the Reagan administration in the mid-1980s and was supposed to bring about an end to the Cold War by making Russian nuclear weapons obsolete, as this invisible shield surrounding the entire continental United States would destroy incoming warheads, okay, before they could ever detonate. Now, many people in the public were quite enamored with this idea, and the defense industry was too, since it would mean huge contracts for the military-industrial complex. There was just one little problem, okay, and that was the technology required to make the system didn't exist. This example will illustrate one of the many problems with the proposed system. So in this example here, we are told that this proposed ballistic missile defense system
calls for a laser that can focus 25 megawatts of light on an attacking warhead. That in and of itself, the laser technology in the mid-1980s, okay, that in and of itself would have been a huge stretch to accomplish. The weapon works by first heating the warhead to the point of destruction, okay, but then it also delivers momentum that alters the warhead's trajectory. All right, so we are asked to first find this. If the beam dwells on a 200 kilogram warhead for 15 seconds, what velocity change does it impart to the warhead? Okay, so given that information, we can start by finding the energy delivered in a 25 megawatt beam acting for 15 seconds. Okay, so simply multiplying the power, the 25 megawatts times the time, okay, by the 15 seconds, that tells us that this beam has a total energy of 375 megajoules. Now, if we assume complete absorption of the energy, okay, and complete transfer of momentum, okay, then we can figure out what that momentum, okay, of the wave and the momentum imparted to the warhead would be. It would simply be this energy divided by the speed of light. Okay, and we do the number crunching here. We come up with a value of 1.25 kilogram meters per second. Now from this, we can figure out the velocity change. So basically taking that momentum change divided by the mass, we come up with a velocity change, okay, of 0.00625 meters per second. So basically less than a centimeter per second. Now that change in velocity would be insignificant, okay, in comparison to a typical warhead speed of 7,000 meters per second. Okay, to see this problem okay, highlighted here though, let's take a look at part B. It says estimate the distance by which the warhead would be knocked off course over its remaining 30 minutes of flight. So this is assuming that we could actually hit that warhead with a laser, okay, 30 minutes before it ever reached the continental United States, before it ever reached the mainland. Okay, that too is a big assumption. And don't forget the fact that at the time, okay, the Soviet Union was in possession of thousands of warheads. Okay, their stockpile was in the order of tens of thousands of warheads. So if we have this velocity change from part A, multiplying that by the time, okay, the remaining flight time, that is 30 minutes, which we'll convert into seconds, tells us that that warhead would be knocked off target by a distance of 11 meters. Now, if you're talking about, shooting a bullet at a person, that might be a very effective strategy. But when you're talking about a nuclear warhead, okay, having that warhead thrown off course by a distance of 11 meters is going to be completely insignificant, okay, in the case of that warhead carrying a nuclear weapon.
Thus far, we've spent a lot of time discussing properties of electromagnetic waves, but we have not asked or answered the question, how do electromagnetic waves get created in the first place? So in this slide, let's explore this fundamental question. The requirement for electromagnetic wave creation, okay, it all starts by having either a changing electric or changing magnetic field. So if we think about what we know about Maxwell's equations, okay, in particular, Faraday's law tells us that in a region of space where the magnetic field changes in time, this will induce or create an electric field. And we know that Ampere's law conversely tells us that in regions of space where the electric field changes in time, this will create or induce a magnetic field. So the bottom line is that a changing field of one type ensures the creation of the other type of field. So that's a start. We now need to take a look at this question of uniform versus non-uniform field changes. So, in other words, what's behind the change? If one type of field changes uniformly in time, okay, then the field of the other type gets created, okay, but it's constant. It doesn't change in time. In other words, if, according to Faraday's law, we have a changing magnetic field, but that magnetic field changes uniformly in time, okay, that will create a uniform or constant electric field. Likewise, Ampere's law tells us that in a region of space where the electric field changes uniformly in time, okay, that will create or induce a magnetic field. Okay, but what happens if one of the fields changes non-uniformly in time? Okay, well, then not only is the field of the other type created, okay, but the creation of that other field, the other field that gets created, is not constant. Okay, it additionally changes in time. Okay, so we'll talk more about this in the next slide, but I just kind of want to give you an analogy here. Okay, think back to what you know from your course in mechanics and motion. Okay, we would say that if an object's position changes uniformly in time, okay, then that object has a velocity, but no acceleration. Okay, if, however, an object's position changes non-uniformly in time, then not only does that object have a velocity, okay, but that velocity also changes in time, which leads to acceleration.
So from the last slide, we can say that the source of all electromagnetic waves is accelerating electric charge. That is, when you have a charged particle that accelerates, okay, it will create an electromagnetic wave. So to review some of the concepts we talked about in the last slide, but to present them a little bit differently here, let's take a look. Okay, if you have an electric charge which is at rest, a stationary electric charge, then we know from our discussion of electrostatics that that stationary electric charge will set up a uniform electric field in space around it. But now let's take a look at the case where that stationary charge is no longer stationary, okay, where it has motion, but where it moves at a constant speed. So for example, let's suppose that this is an electron in a wire, okay, that is moving in the form of a DC steady state current. So it's moving at a constant speed. Okay, well now we can say that the electric field it sets up is now changing in time. Okay, we have a uniformly changing electric field as that charge moves at a constant speed. And that uniformly changing electric field will create a uniform magnetic field. So if you look at Ampere's law, if you look at the right-hand side of Ampere's law, it tells you that when the electric field and therefore electric flux changes uniformly in time, that is when d phi dt is constant, then a uniform constant magnetic field is created. That's what the left-hand side of Ampere's law tells you. So we now want to look at what happens when you have an electric charge which not only moves but now accelerates. That is when its velocity is not constant. So hopefully you can reason that if that charged particle moves at a constant speed, okay, it creates a uniformly changing electric field. When that particle moves at a non-constant speed or accelerates, okay, it now creates a non-uniformly changing electric field. And, okay, according to Ampere's law, if that electric field, okay, changes in a non-uniform way, changes non-uniformly in time, then that means that the magnetic field that gets created by it also must change in time.
So what I'm showing you in this slide is a rather simplified explanation of the process of electromagnetic wave creation that comes from the cartoon book of physics. Take a look. Okay, it is quite simple, but it nicely illustrates the idea that we introduced on the previous slide. You may want to pause the video at this point to look at it in greater detail.
So we'll now take a look at an actual piece of technology used to produce electromagnetic waves, that of the half-wave dipole antenna. So you see here in the slide, there is a picture of that dipole antenna, and it will be connected to an alternating current power source. So let's take a look at how this works. So the dipole antenna consists of two conducting rods that are connected to an AC generator. So basically what that means, and if you look at this picture, is that for half of the cycle, the current in these rods will be in one direction, whereas half a cycle later, the current in these rods will be in the opposite direction. So we can think of this when the current is in one direction. In this direction, we can think of the top rod as being positively charged, the bottom rod is negatively charged, and vice versa in this picture when the current changes direction. So you can see here that as the polarity of the rods alternates from plus to minus at the same frequency as the AC source itself, that these charged rods produce electric field lines that are very similar to that of the electric dipole. If I can think of this top rod as positively charged and this bottom rod as negatively charged, we know that the electric field lines go from the positive charge to the negative charge. Really in this case from the positive rod to the negative rod. Now half a cycle later, when the current switches direction, we now see that these electric field lines are reversed in direction. If the positive charge is now the bottom rod, the electric field lines reverse direction. But in order to do that, because fields are continuous, what we really get is these field lines don't stop. When the field changes directions, we get the field lines to fold back on themselves, to form these closed loops. Also notice that these these rods with changing current also produce magnetic field lines around them. So for the top picture right here, where the conventional current is upwards, hopefully you would agree that these magnetic field lines that encircle the rods should be directed like this. If you use your right hand current rule, place the thumb of your right hand in the direction of the conventional current, you will see that on the right hand side of the rod, the magnetic field is directed into the plane of the screen, whereas on the left hand side of the rod, the magnetic field lines would be coming out of the screen. And of course I can't show you these closed continuous loops, but magnetic field lines always encircle their sources, forming closed loops. So when the current changes direction, the electric and magnetic field lines change direction too. Now we've already taken a look at the electric field lines, but let's take a look at the magnetic field lines in the bottom here. So here, when the current is in the opposite direction, you can see using the right hand rule that the magnetic field must go into the plane of the paper on the left hand side of the wire now, and it must come out of the plane on the right hand side. So as we said, these electric field lines, they fold back on themselves, they form closed continuous loops, and we know that magnetic field lines always form closed loops. So hopefully you can see here that the end result is that you get these electric and magnetic field lines which close on themselves and will propagate outwards at the speed of light. Okay, that is an electromagnetic wave. Remember, an electromagnetic wave is nothing more, okay, than this oscillating pattern of electric and magnetic field vectors, okay, that carry energy with them as they travel through space. When you get very far from the source, let's take a look at what happens. When you're very far from the antenna, the electric and magnetic field lines, okay, the wave fronts appear very flat. So you can kind of see here the flattening of that wave front. And we can think of them as plane waves. And very simply, since waves carry energy, as you get further away, okay, the magnitude of the fields, the electric and magnetic fields, okay, get weaker with distance. Okay, they vary inversely as distance. So you can imagine that as that wave travels outwards, its energy gets distributed to a greater region of space. Okay, so the magnitude, okay, of the field at any point in space, okay, becomes weaker with distance. So if all electromagnetic waves are produced by accelerating electric charges, let's take a look at some other examples. So our first example may not be that new. If we look at radio waves that are emitted from a radio transmitter, well, as we saw in the previous slide, we have electrons which move back and forth in an antenna, okay, as a result of some sort of alternating current. And you see here we have a source of accelerating electrons. And of course, the degree of the acceleration, the magnitude of that acceleration will tell you something about the energy of the electromagnetic wave created, as well as the frequency and where it falls on the electromagnetic spectrum. So very shortly we'll learn that radio waves, these are low energy electromagnetic waves. Okay, low energy, low frequency waves. When you go to the dentist's office and you have an x-ray taken of your teeth, okay, well, what's going on there? Well, in the case of an x-ray machine, you have high energy electrons which are first, okay, created or accelerated to high speeds and then allowed to slam into usually a tungsten target. And when they do that, when they slam into the target, they decelerate very quickly. And because of that rapid or large deceleration, okay, they create a high frequency, high energy electromagnetic wave in the X-ray portion of the spectrum. When you open up your microwave and put in food containing water to heat it up, what's going on there? Well, the microwave, your microwave contains a device called a magnetron. And in the magnetron, you end up with electrons that are forced to move in circles under the action of a magnetic field. And you know that any time you have a particle or object that moves in a circular path, it accelerates. So in the case of these charged particles, these electrons, they're experiencing a centripetal acceleration. And that acceleration creates microwaves. It creates electromagnetic waves in the microwave region of the electromagnetic spectrum, okay, fairly low energy waves. What about when you take a look at a neon sign? Okay, what's going on there? Where are the accelerating charged particles? Well, if you think about a classical picture of an atom, okay, as those electrons are being excited in the neon atom, okay, as they are absorbing photons and moving up to higher energy states, okay, those electrons in a classical sense, okay, are experiencing an acceleration. And that acceleration is what produces light of this characteristic red color and wavelength and frequency. The piezoelectric effect, I'm not going to demonstrate it for you here, but we'll take a look at a schematic of it. It turns out that when you take many types of crystals and you subject them to pressure, okay, the pressure applied to the crystal causes charges within the atoms to vibrate. And this generates a low frequency electromagnetic wave.
Let's formalize a concept that we briefly introduced in the last slide related to the frequency of the electromagnetic wave that gets produced. We'll start by revisiting what we know about mechanical waves. Now, for mechanical waves, we can say that the frequency of the wave created will exactly match the frequency of the disturbance to the medium that created the wave. So, very simply, for example, if you want to create a certain sounding note on a guitar string, okay, you can say that the frequency of the vibrating string is going to match the frequency of the sound wave produced. It's really not that much different for electromagnetic waves. Okay, we can say that the frequency of the electromagnetic wave will be determined by the frequency of the accelerated charge that creates the wave. With regards to nomenclature, we name electromagnetic waves based on where they fall on the spectrum of wavelength and frequency. Note that the specific names of waves correspond to ranges of wavelengths and frequencies, okay, rather than to individual wavelengths and frequencies. So in looking at the spectrum, you certainly should not memorize the actual numbers for wavelengths and frequencies, but you should be somewhat familiar with their chronology. Okay, that is, for example, that a radio wave is longer in wavelength and lower in frequency than any wave of light, let's say, that is visible to the human eye. Also, don't forget what you learned about the relationship between wavelength and frequency in the unit you did on wave theory, okay, where you were talking about mechanical waves. In other words, that there is this inverse relationship, okay, between the wavelength of the wave and the frequency of the wave. And you can see in the illustration that as you move to the left in the picture, that the wave frequency increases while the wavelength of the wave decreases. So high frequency, high energy waves are small in wavelength and vice versa. Okay, by contrast, when you look at the radio end of the electromagnetic spectrum, okay, you see that wavelengths can vary from several meters, okay, when we're talking about FM radio waves, to hundreds of meters when we're talking about AM radio waves. Okay, so these long waves, these long wavelength waves in the AM portion of the electromagnetic spectrum are low energy, low frequency waves. Let's take a look at a few sample problems involving the electromagnetic spectrum, where you'll first have to recognize the nomenclature, okay, be familiar with their chronology, and know something in general about the properties of electromagnetic waves. So when we take a look at this first question, where I was, how is a gamma ray physically different from a radio wave? Okay, well, when you look at the electromagnetic spectrum, you can see that gamma rays and radio waves are on opposite ends of the electromagnetic spectrum. They have very different frequencies, wavelengths, and energies. Okay, gamma rays are very high energy waves, okay, high frequency waves, okay, whereas radio waves are very low energy, low frequency waves. But, you know, in terms of what creates the waves, okay, well, we know that all electromagnetic waves in general are created by accelerating charged particles. So they certainly have that in common. Okay, but, you know, if we want to answer this particular question, we're asked what makes them different. Okay, really it's just a matter of their wavelength, frequency, and the energy that they possess. So in this next question, we're asked which has a smaller wavelength? A wave emitted from your microwave oven or a wave emitted from the infrared heat lamp keeping your hamburger warm at McDonald's? Oh wait, that's right, McDonald's claims that they don't use those infrared heat lamps. Okay, well, at any rate, Okay, to answer this question, this requires that you have some familiarity with the chronology of the electromagnetic spectrum. And when you look at it, okay, you can see that the infrared wave is going to have a smaller wavelength and higher frequency than a microwave. So here, understanding the chronology allows us to answer this question. Okay, in this last question here, we're asked, what would you rather be hit with? A radio wave produced by Modesto's radio station KHKK, okay, that is 104.1 FM, the Hawk, okay, or a gamma ray. Well, the 104.1, okay, that really refers to the frequency of that wave, okay, frequency of 104.1 megahertz. Okay, well, once again, okay, in order to answer this question, you need to, look at the electromagnetic spectrum, and when you do so, you can see that radio waves are fairly low energy waves, whereas gamma rays on the other end of the spectrum are higher energy waves. So if a radio wave passes through your body, okay, it's not going to really produce much damage. But when a very high energy wave like a gamma ray or an X-ray passes through your body, okay, well, these waves, because of the high energy they possess, okay, they can wreak havoc on the cells in your body, which can ultimately lead to cell mutations and various forms of cancer.
All right, so just a few more examples of problems related to the electromagnetic spectrum. So, okay, letter D here is really a follow-up from the previous problem. It says, what does that number 104.1 on your radio dial mean anyways? You ever wonder that? Well, that 104.1 is really a measure of frequency measured in units of megahertz. FM waves are frequency modulated waves, and they are measured in megahertz. They're higher frequency waves than AM radio waves. These are amplitude modulated waves that are measured in kilohertz. So those numbers are really measures of frequency. This question says, which has a higher frequency, the wave emitted from the radar gun of the police officer who is about to issue you a speeding ticket, or the wave that causes you to tan or burn, depending upon your skin type, while basking in the sun? Once again, to answer this question, you have to have some familiarity with the chronology of the electromagnetic spectrum. So it turns out that the ultraviolet wave causing you to tan is a much higher energy wave, okay, than the radar wave coming from a radar gun. And lastly, it says your text fails to introduce everyone's good friend, Mr. Roy G. Biv. Who is this mystery man, and why should he become your friend too, if he's not already? So I'm guessing that some of you have met Mr. Roy G. Biv at some point in your science education. Okay, well, Mr. Roy G. Biv, that is the acronym for the colors in the visible portion of the electromagnetic spectrum, right? So as this illustrates, red, orange, yellow, green, blue, indigo, violet. That is a good way to remember the chronology. Red, the red end of the visible spectrum, these correspond to a range of light waves which are longer in wavelength than the violet end of the spectrum and lower in frequency.